more hurtful than helpful if they do too much of the work, you know. Like I was a tutor for a while. I used to I had about 10 hours a week of tutoring I did, and you know, some of it I thought was good. Others I told the mom who was paying me, I was like, stop, don't waste your money, unless your children, you know, unless these boys, unless they stop playing video games, you're wasting your money. No amount of math that I tell them will help, because the only thing that's going to help is for them to stop spending every waking moment of their life playing this video game, you know. So, I mean, I've heard all kinds of horror stories about trouble with drugs and alcohol and things like that. You know, growing up, I grew up in the 80s. It was the just say no, you know, this is your brain on drugs, all this. There was so much anti-drug, you know, information always sort of pushed at you. No one ever said, you know, this is your brain on video games, but it's a much more real danger for a lot of students, the danger of, you know, overindulgence of video games. Well, and they've got some pretty awesome video games right now, right? So, danger's real. Okay, so we talked about polynomial graphing, right? And so, how do we do it? So basically, given f of x, a polynomial, we factor f of x completely, then that tells us where the x-intercepts are, right? And if they bounce or not, right? So basically that's the story, right? I mean, you have a polynomial, you try to factor it completely. If, you know, after you factored it completely, so just let me write an example. So if we had f of x, you know, x to the fourth minus 81, we could factor that completely, right? How would we factor this completely? We go, that's x squared minus 9 times x squared plus 9, right? And can we factor that? Well, x squared plus 9 we cannot factor further, right? That's like irreducible. You can't break that down more without complex numbers. But the x squared minus 9 we can still do better, right? That's x minus 3 times x plus 3 times x squared plus 9. And I'm like, did I ever hit record? I can't remember. Oh, I did. Good. At this point, we're done, right? And so from this tells me, you know, 3, 0, and this tells me minus 3, 0 are points on the graph, right? Those are the x-intercepts. What's the y-intercept? Just plug in x equals to 0, right? What do we get? Is it 0 to the fourth, right? Minus 81, also known as minus 81. And how about these x-intercepts? Does the graph cross, or does it bounce at these x-intercepts? What do you think? Cross or bounce? Yeah, wait. And while I'm asking you that, I'll ask you another question. Is there anything else interesting about this function that makes it like especially easy to graph? I mean, I would point out it's just the y equals x to the fourth function dragged down 81 units, right? It's just a vertical shift down of the quartic y equals x to the fourth, you know? I'd also point out it's an even function, right? F of minus x is equal to f of x. It's even. So that means that like the picture of it should be symmetric about the y-axis. So what do you guys decide whether or not it crosses or bounces? It bounces, yeah. Oh, no, well, sorry, nope. No. And I'm not going to use the same scale here, obviously, because like, you know, 81. And I'll put 3 here, minus 3 over here. But no, it crosses because it's just an odd factor. Like if we have x minus whatever, x minus the root to an even power, it bounces. If we have x minus the root to an odd power, it crosses. So these are just the first power. So it's going to change sign. It's going to go across the axis at 3 and minus 3. And so, yep, this thing just basically looks like this. There you go. Now, if you can graph this polynomial, you can also solve related questions, right? Like, can you tell me when is x to the fourth minus 81 negative? Could you solve x to the fourth minus 81 less than 0? I mean, if you've already made the picture, you should be able to see from the graph it's negative where? Yeah, between negative 3 and 3. Of course, we could also see that from our sign chart idea, right? We draw the number line, we put, you know, marks at the algebraic critical numbers, put pluses and minuses like we did before, remember? All right. Example 2. What if I had f of x equal to x squared plus 3x minus 4 quantity squared? I wanted to graph that. So again, my first thing I want to do is I want to factor this completely, right? And so I would factor what's inside the square, which is what? X plus, well, maybe x plus 4 times x maybe minus 1. Would that work? All right, now I got to square that, right? So when we square a product, we square the factors in the product like this, x plus 4 squared, x minus 1 squared. Okay, great. Now it's factored completely. So we have X-intercepts at x equals to minus 4 and 1. What's my y-intercept? F of 0? Yeah, 16. Very good. I think I have everything I need to make the graph. Let's see here. Where is he? Minus 1. Oh, rather 1. Can you tell me anything about this function? If the formula is a square, right, One of the things you might notice is, what's that? It's a circle? No. Well, okay, so you guys tell me, these x-intercepts, is it going to cross or is it going to bounce at these x-intercepts? Bounce, right, because we've got squares. So these both bounce. In fact, if you look at the original formula, you should be able to see immediately that this is greater than or equal to 0 because it's all a square. If I have a real number squared, it's non-negative, right? So I can't, there's no way this formula gives you a negative number. But it bounces off 4 and 1, and so it looks something like this. Sadness. Well, that's not right. That's not right. Okay. Let me try again. I mean, I can't double back on myself. I can't, fail the vertical line test. It's too horrible. Here, I'll just make a picture and forget about the scale here for a second. So this one is at -4. This one is at 1, 0. And wherever the again, I don't really know for sure where that maximum is in the middle without doing a bunch of numerical work. In other words, plugging in more points. I mean, I can tell you it crosses the x-axis, the y-axis at 16, but actually where that peak is, I'm not really sure without further investigation. I'd actually have to plug in some points, plug in, f of a half and f of -1 and see what happens. All right. But this is enough for us. I just, I would say probably the instructions are something like graph the polynomial, be careful to, accurately depict any x-intercepts and the y-intercept. And then if I said that much, this would be a correct answer up to those instructions. Of course, you could use a graphing calculator and check our work, right? You are allowed to do that. Okay, so this is graphing polynomials. All right, we factor completely, and we just look for x-intercepts, look at the y-intercept, maybe throw in a couple of more points to get a better sense of scale. That's pretty much it. Now, of course, the next topic is not just polynomial graphing, but graphs of rational functions, right? I tell you, I'm having trouble with this board. I think it's time for me. I got one in storage. I just need to actually get over there, and I need to screw it to the wood here, and it'll take me a couple hours. As long as I write in black, you guys can still make this out, right? If you can't understand what I'm writing, please let me, know. So graphing rational functions is, have we done any of those yet in here? I don't think I've started yet in here. Maybe one. I think I did one. Definitely some of you weren't here when I did it anyway, so let's start again. How do you graph rational functions? So, new features that we haven't dealt with in polynomials. Well, we have horizontal asymptotes. We have vertical asymptotes. And we also have holes in the graph. These are all things we have to learn how to deal with So I'll just abbreviate the first one, ha, and the second one like that. And again, so here's the goal is to graph f of x equals to p of x over q of x. This is a rational function, all right? So I can tell you at the start, oh, we did one of these, right? But I accidentally did one with a slant asymptote. Remember that? And then I said, oh, oops. I'm not sure if that's allowed in here or not. I went and talked to some other instructors. It is not allowed. So that slant asymptote example we did is beyond the course, all right? So that example was free. For us in here, what we're going to focus our attention on is the case. So we're going to have where the degree of the denominator function is larger than or equal to the degree of the numerator function. So this is the denominator polynomial, and this is the numerator polynomial. And I can tell you the story about horizontal asymptotes at the start, all right? So let's get that done with. So what can I tell you about horizontal asymptotes? How do they work? So if the degree of q of x is greater than the degree of p of x, then y equals to p of x over q of x has y equals to 0 as horizontal asymptote as x goes to plus or minus infinity. What that means is that eventually, in this formula, the denominator completely dominates the formula, and it makes it go really, really close to 0. All right. Now, horizontal asymptotes, we can cross horizontal asymptotes. The graph can go across a horizontal asymptote. It's allowed. All right. But long term, it tends to not cross it. It tends to kind of just approach it very long term. But when you're close to the origin, the graph can actually go across the asymptote. All right. That's only true for horizontal asymptote. For the vertical asymptote, you can't cross it. All right. We'll get back to that soon. What's the other case? Either the denominator is larger than the degree of the numerator, or what else can happen? They're equal, right? So if the degree of q of x equals to the degree of p of x, then we look at leading coefficients. So let me expand on that. In other words, f of x is equal to, say, like an x to the n plus an minus 1 x to the n minus 1 a1x plus a0 divided by b n x to the n bn minus 1 x to the n minus 1 b1x plus b0. So I'm giving you like the coefficient breakdown of the polynomials, right? They're polynomials, they have a formula like that, right? And if they have equal degree, then they have the same kind of leading term. They both have like an x to the n and bn x to the n. In this context, the only thing that matters to the horizontal asymptote is just the leading term. Like this one right here and that one right here, that completely dictates what the horizontal asymptote is. If that's the case, this has y equals to an over bn as the horizontal asymptote as x goes to plus or minus infinity. And so those are the two possibilities for the graphs of rational functions we're going to look at. We'll either have a horizontal asymptote of 0, or we have a horizontal asymptote which is just a constant where it's formed by the ratio of the leading coefficients. All right? So next up, let's talk about the vertical asymptotes and the holes in the graph. And what these are new features. What's an old feature? What two old features have we already looked at for rational functions? Excuse me, for polynomials. And technically speaking, by the way, guys, polynomials are also rational functions in a sort of silly sense. In fact, to be technically honest with you, we do also graph the case that the degree of the numerator is larger than the degree of the denominator, but we insist that the denominator is just the number 1 in the case that we study. That's polynomials. Like polynomials are just when q of x is equal to 1. We do talk about that. Anyway, let me stop with my confusing if. I mean, it might be correct, but it's probably not correct to say it here, what I just said. So my point to you is these are new, but we can also still think about what? The y-intercept and x-intercepts, right? Those are still interesting for graphs of rational functions. We'd still like to know where the graph crosses the x-axis and where it crosses the y-axis, right? So let me just point out that, to make this list, also old, we should still care, y-intercept. How do we get that one? That one's easy. That's f of 0, right? And x-intercepts, well, x-intercepts are a little bit more complicated. All right? So here's basically let me give you the big picture of what goes on here. So we have f of x equals to, stuff times x minus some root to the, let's say, I don't know, n power. And then we've got stuff. And then we've got x minus that same root to the d power for denominator, right? And here, the stuff does not have x minus c as factor. So what I'm trying to say is you take the formula for the rational function and you put all of that factor into x minus c, all right? Then if that's the case, there are different possibilities, all right? So here are the cases. 1, if d is strictly greater than n, then x equals to r is vertical asymptote. Can't spell. All right. If the denominator factor is strictly larger than the numerator factor, it wins. It makes the thing blow up to infinity as we cross x equals to r. In fact, well, in all of these cases, the number r is not in the domain of the function. All right, so for all of these, r is not an element of the domain of the function, right? Because if you look at it, the number r gives us division by 0 in the formula, right? So that means that r is not in the domain of the domain of the function. So if d is greater than n, we get a vertical asymptote. Do you have a question? Okay. What happens if d is equal to n? Well, let me deal with the case d is less than n for a second here. If d is strictly less than n, then, r comma 0 is a hole in the graph. And 3, If they're equal, then f reduced of x, which is equal to stuff over stuff. In other words, we've removed the x minus r factor, and we're just left with whatever was there besides that. All right, gives r comma f reduced of r is whole in graph. Reduced. You could say f red if you like. I mean, it doesn't really matter. What I'm saying is you take the function that you have and you cancel out the x minus r factors. That gives us the reduced function. Beyond this, we maybe make a sign chart to kind of guide our way. That might be helpful, right? And of course, we can always add, we can evaluate the function at points to, give us further insight. So, sorry, I know it took me a few minutes to actually get that all out in front of us, but it's really for the best. If you watch the videos from the other section, which for some reason is way ahead of you guys at the moment, I don't know exactly how it happened, but it's just the way the test ended up being timed and junk. It's that assessment day, that's part of it, definitely. For them, I kind of discovered all of this example by example, and only at the end of a bunch of examples did I come and say with authority, hey, this is exactly what happens. These are the different cases, So you guys have the advantage of everything I've learned from teaching them, and hopefully this helps us make it easier in here, because we know this is the game plan. This is the template. This is how we can expect things to work out. But to be honest, before we can do anything with any example, first step is we have to completely factor the denominator and the numerator polynomial. All right? So now that we have this all in front of us, let me work an example over here. This one will be very silly. It's almost too silly. This function is what? Right. And so I guess I should add to this is what we're going to want to do is we're going to want to make a list of all the numbers where either the numerator or the denominator could be 0. All right? We'll think of those as our sort of critical numbers for the rational function. This one just has a critical number of 3, right? 3 is not in the domain of this function, right? So this is equal to what? This is equal to 1 if x is not equal to 3, right? And it's just, not defined if x is equal to 3, right? How would you graph that? It's 1. Except at 3, where what? We have a hole in the graph. So that is an illustration of case 3. In this example, the reduced function is just equal to the number 1. When you cancel out the factors, that's the reduced function. Let me do another one that's less silly. What if we have f of x equal to x minus 3 over x squared minus 9? Okay, now we've got something to do, right? We need to say, okay, well, that's x minus 3 over x minus 3 times x plus 3. So now our numbers of interest here are critical numbers, interesting numbers, if you like. So 3 and minus 3, we need to study, right? Now x, yeah, so what's that? Yeah, so yeah, if we plug in 3, we get 0 upstairs, right? But the trouble is we also get 0 downstairs, right? So here's the situation. In this one, the number 3 fits into case 3 again, because we have a linear factor both in the numerator and in the denominator. So this is going to have a hole in the graph at x equals to 3. And what's my reduced function this time? So basically cancel out the x minus 3, we're left with 1 over x plus 3. That's my reduced function in this case. So where's the hole in the graph? At y equals to what? F reduced of 3, which is 1 over 3 plus 3. In other words, the reduced, we get a hole at 1/6, at 3 comma 1/6. Ah. And what about x equals minus 3? See, in that we're fitting into case 1, because we just have x plus 3 in the denominator. There's nothing to oppose it upstairs. That's not a hole in the graph. That's just straight up. That's just going to blow up to infinity. There's nothing to oppose this when we plug in minus 3. That's just a vertical asymptote. And so that's all I need to graph. I can graph it now. So I mean, it's something. I guess I shouldn't say it's all I need to graph it. I mean, can you guys tell me what the horizontal asymptote is in this case? Remember, there are two cases. Either it's a constant or it's 0. I mean, either it's the constant 0 or it's the non-zero constant formed by the ratio of the leading coefficients. This one, the denominator is quadratic, the numerator is linear, so that means the denominator is going to win. It has a horizontal asymptote of what? Horizontal. Yeah, I mean, I agree, vertical asymptote at minus 3. But the horizontal asymptote in this one is 0, because we have a quadratic in the denominator, and that's going to win after a while. Think about plugging in 1,000,000 into this. You plug 1,000,000 into this, you got like 1,000,000 upstairs, but you got 1,000,000 squared downstairs. So it's very close to 0 for large values, either in the positive or negative sense. What was the what's the y-intercept here? Forgot to calculate that. F of 0 is minus 3 over minus 9, right? So the y-intercept is 1/3. Let's suppose I'll put that like here. And where was the hole in the graph? We said the hole in the graph is at 3, comma 1/6. 1, 2, 3. So it's like about right there. So the graph, remember, it goes like asymptotically to 0. Got that hole right there. Crosses through the y-axis right there. and then it blows up to infinity as you get close to the vertical asymptote. Over here, it does like that. And that's the graph. Now, your graphing calculator will do a pretty good job on a lot of this, but what it won't probably do a good job on is holes in the graph, right? You'll have to understand those for yourself through the factoring. Like I'm pretty sure if you tried to graph this with the graphing calculator, it would show most of what I just did, but it might do some kind of, I don't know, I'm not sure what it's going to do at 3. Either ignore it or do something crazy there. I'm not sure which. It depends on the particular programming of your calculator. Let's see here. How about example 3 on rational functions? What if I have something, excuse me, like f of x equals to, I don't know, x squared plus x to the 4th divided by, you know, x cubed plus 6x squared plus 9x. And I meant to put a, well, we'll stick with this. It's fine. It's fine. So I can tell you this much. Oh, I can't do that. My apologies, guys. I can't do that. Why? I would have a numerator which has degree 4. I have a denominator which has degree 3. This is out of bounds. This would have a slant asymptote. I have to modify the example a little bit. I'll throw in a, oh, I don't know. You guys give me anything you want. What do you want? X minus or plus something. What do you want to put here? Choose your own adventure. It's your chance. What? 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 All right. It was probably another math class that's more important than this one. I know that your life revolves around math, so I have to keep that in mind. But no, it's fine. You can always watch the video later. Let's see here. So how about plus 2? Would that be good? I'll do, yeah, fine, plus 2. I'm going to do minus 2, actually, just to keep things separate. All right, so the first order of business is to factor everything so we can see clearly what we're facing, all right? So there is a x squared that factors out of upstairs. We get 1 plus x squared. And downstairs, I can get an x, and then that's x squared plus 6x plus 9. X minus 2, well, that's fine. That just sits there. Oh, but x squared plus 6x plus 9, we can factor that, right? How's that factor? X plus 3 squared, yeah, times x minus 2. So let's talk about all the different players in this game here. Let's talk about each one of them separately, and let's talk about how they contribute to the story. Sorry about that, people at home. it's all Heaven's fault, right? She's just left me so beside myself with her leaving like that. I'm just still recovering. I should be used to it by now. Oh, it's fine. So my point here is we've got like, this x squared kind of term that suggests x equals to 0 is an interesting factor. 1 plus x squared suggests what? The x downstairs also says look at x equal to 0, right? The x plus 3 squared downstairs says we should look at x equals to minus 3 as an interesting point. The x minus 2 suggests that x equals to 2 is an interesting point, right? How about 1 plus x squared? See, that actually doesn't matter in some sense. It doesn't give us a 0, right? 1 plus x squared, it cannot be factored. So that pretty much just says whatever. I mean, so not interesting. I guess it's interesting in that it's not interesting. Those kind of factors don't give you holes in the graph, they don't give you zeros, and they don't give you vertical asymptotes. They just sit there and sort of multiply the values in a somewhat interesting way, but that's it. So in this case, we're actually finding ourselves in case 2. Case 2 here. So x equals to 0 fits into case 2. Of my discussion about cases over there, because we have, x squared over x to the 1. So this says that 0, 0 is hole in graph. All right? That's what that means. Now, well, anyway, yeah. Now, you guys tell me, what about, so that's what happens with 0. What about minus 3? What's the story for minus 3? So the only thing to worry about is that, right? So if the factor just appears in the denominator, game over, it's a vertical asymptote that it's going to contribute, So we get is vertical asymptote. And how about the other one, x equals to 2? Likewise, it's a vertical asymptote because the only thing to look at is just that factor right there, right? So there's nothing that can counterbalance it to make it turn into a hole in the graph, So, okay, so now I can make my graph. I guess, oh, I have said something. I've said that the y-intercept is f of 0. This is the counterexample to that comment. F of 0 is what? F of 0 is not defined because f of 0 gives you 0 over 0. This is undefined, right? So technically this actually this graph doesn't even have a y-intercept. It has a hole in the graph at the y-axis. So that's kind of funny. So I'll attempt a picture of this guy. Let's see here. Where are the interesting numbers? We have a hole in the graph at 0. We have a vertical asymptote at 2. And we have a vertical asymptote at minus 3. All right, great. So how do we decide? And what about the horizontal asymptote? We have what, degree 4 over degree 4, right? So you have to think about if I multiplied this out, right? If I multiply, you don't actually have to do it, but think about multiplying it out. What would the leading what would the, let me write it up here. So basically, if you think about it, x to the 4th, right, plus stuff. And downstairs, you've got x to the 4th plus stuff, right? So horizontal asymptote equals to what? Yeah, I don't actually want to write. I don't actually want to multiply them. We don't. It's irrelevant. You don't need to multiply it. You don't need to multiply the denominator out to see that the leading coefficient is what in the denominator? It's 1, right? Because the leading coefficient comes from the x cubed times the x, right? Now, I mean, if this factor we had written here, if this was like 2x minus 4 or something like that, then the story would have been different, right? The leading coefficient might not have been 1. It could happen that it's not 1. But this one, the horizontal asymptote, is just y equals to 1. So I'll even put that in here. Again, the horizontal asymptote doesn't mean much, except far on out. Far on out, we should like tend to that value, whatever else happens. So how did I start my graph then? See, at this point, we should plug in a number, right? So to get started, plug in a number, maybe. So now I would say, plug in some points. So can you guys tell me? I would suggest we plug in, I don't know, like x equals to 1 is always easy, right? What's f of 1 equal to? 2 over 1 plus 6 plus 9, which is what? 16? Times what? 1 minus 2 is what? Minus 1, right? So minus 1/8 is the value of the function at 1. So at 1, it's like here, right? And what if we plugged in minus 1? What would that give us? Yeah, I've got 2 upstairs, right? Because minus 1 squared plus minus 1 to the 4th is 2. And downstairs I've got what? I've got a minus 1 plus 6 minus 9 times minus 3. What's that work out to? 2 over 12? I think you're right, because like 10, minus 10 plus 6 is minus 4. Minus 4 times minus 3 is 12, 2 over 12, aka 1 over 6, right? So it's, like in here somewhere, up to the limits of my artistry. So apparently it's kind of like crossing the x-axis here, right? What happens with the vertical asymptotes? It blows up, right? Or blows down. So I can see then, it has to go to infinity at the vertical asymptote, so it's got to do something like this. Now the reason I know it does something like that is we've already accounted for all possible ways it can only change from positive to negative either at a 0, right, or a vertical asymptote. But we've already taken care of all the zeros and all the vertical asymptotes, right? So once I figure out it's positive or negative between two of those features, it has to stay that way. So the fact that this point here was negative means that the function has to stay negative to the right of that hole in the graph and to the left of this vertical asymptote. And likewise over here, once I figured out that's positive, the function has to be positive between that hole in the graph and this vertical asymptote. So that forces me to do this. Like that. Right? Now, at this point, you can either plug in points to the left of -3 or to the right of 2, right? Or you could let me tell you a theorem that would kind of guide your thinking. And so remember how we learned that if it's even, it bounces, and if it's odd, it crosses? There's kind of a similar rule for asymptotes. If you have like division by an even power unopposed, that asymptote kind of bounces. It's like a volcano. Whereas if the asymptote is created by an odd power, it's going to change. It goes from infinity on one side to minus infinity on the other, vice versa. So like this one, I have an x minus 2. That's like an odd 0. It's analogous to an odd 0. It kind of is a crossing. It'll cross the axis there. In other words, you're going to minus infinity from this side, but you're going to plus infinity from the other side, like that. And then the horizontal asymptote is what it tends to, like that. In contrast, over here, that x minus 3 comes from x plus 3 squared. So it doesn't change signs. It doesn't change signs across x equals minus 3. It stays the same sign, which is to say it's kind of like a volcano over here. Now, of course, you could double check me by just plugging in like -4, right? Maybe we should do that. What is f of -4? Ugh, it's unpleasant is what it is. I guess we could use like one of these formulas that would make it easier, right? So it's like -4 times 1 plus 16 divided by 1 squared. Well, minus 1 squared, fine. Times -6. So I've got like -4 times 17 over -6, which is, anyway, the point is it's greater than 0. And so, yeah, great. And I think if you look at that number, fine, what is it? It's 2 times 17 over 3, which is 34. 34 over 3, which is like 11.333-ish. So obviously my picture here isn't quite doing it justice. It's like way further up, right? Like my picture is not correct in terms of like where this line is. It's actually supposed to be more like, well, to the scale I'm drawing things, it should be like up here. So, but I don't, if I have a question like this on the test, if you have this general shape right, I'm not going to give you full credit, so the instructions would say something like, graph the rational function, include any vertical asymptotes, and sketch the general shape of the graph, include any holes in the graph if there are any, label them. So I guess I'd lose a point because I haven't labeled my hole in the graph yet, 0, 0. But maybe I wouldn't take a point out there because the origin is kind of a special point in the sense, do you really need to label the origin as 0, 0, or do you know? I mean, that's kind of a very special point in the sense that I don't need to label the origin because you already know the origin is 0, 0. Almost any other point requires a label. The origin's special. Let's see here. Any questions? Now, can we check our work? What's a good way to check our work? Graphing calculator? Sure. But is there another way? I mean, there are many ways, but one way that might be fun, you guys have to tell me the formula here. What is the formula? I'll write it down here. X squared plus x to the fourth, excuse me, divided by x cubed plus 6x squared plus 9x times x minus 2. Can you get the lights for me right quick? Thanks. Oh, goodness gracious. X cubed, 6x squared, plus 9x That's it, right? So there is what it looks like if you do the, the scale properly. Right? And you notice what the graphing calculator fails to do? And this is a very good one, I mean, this is way, way better than like your, Texas Instrument or whatever. See what it didn't do? It didn't tell you that there's a hole in the graph here. So here, let's try some other examples while we got this thing out. What would happen if we look at the graph of like 1 over x squared plus 1? See what that is? So what about this one? Does this make sense given what I've talked about today? 1 over x squared plus 1. Is there any vertical asymptote? Nope. Is there any 0? Nope, because the only thing we have is that x squared plus 1, right? So it just has a horizontal asymptote of what? Of 0, right? Because the denominator has order 2, whereas the numerator has order... what happens if I put a cube here? Why does that happen? Well, what does x cubed plus 1 factor as? Remember, that's the same as, I could rewrite that as x minus 1, x squared plus x plus 1. Same function. See that? So that is x cubed minus 1. But from this formula, you could graph it by hand, right? You could see that this quadratic right here is not